Hi students, in this video's lectures I'm going to show you how to solve statics problems in statics, and there are a couple of problems I'm going to solve it both in a two-dimensional and a three-dimensional. This would help you to understand coordinate system, sign convention, free body diagram, resolving forces in 2D and 3D, and also the equilibrium equations in static conditions. This is in this exercise I will show like a couple of two or three problems. Just to follow it very carefully, this would be a very helpful video lecture for you to perform well in the examination. So let us look at basically in a static equilibrium condition, the net force is zero. They express there are in 2D there are two independent equations in x direction, y direction. The sum of the forces equal to zero, and the perpendicular parallel direction depends on what kind of problem we going to solve it. Look at in 3D, the sum of the total force acting and the system is zero because it is in a static equilibrium conditions. Look at that F in the x direction, y direction, z direction, independently the forces are zero. Let me tell you that the above equations, the previous discussion, it's about you can apply this equation to the particles or body. Suppose if you are dealing with a rigid body in equilibrium condition, static equilibrium condition, you should satisfy not only that three equations in a space, you also satisfy external forces and moments are balanced. Will impart no translational or rotational motion to the body in a rigid body static equilibrium condition. So the sum of the force, sum of the moment should be zero. So it will give us six equilibrium equation in a rectangular, or you can take a three-dimensional coordinate system, Cartesian coordinate system. So what I am talking about a free body diagram. First of all, just look at the coordinate axis, x-axis, y-axis, z-axis. The forces, if the force is acting in the direction of y-axis, along that direction, it is a positive. Similarly, the forces acting in the z direction, this direction, is a positive, and the x direction, this is a positive. If this is act against this direction from origin to x, it is a positive. Origin to y is positive. Origin to z is positive. But if it is in the other way around, if the force act from the y to origin or downwards, that is a negative direction. If it is from the x to the origin or away from that origin, that's a negative, and similarly z to origin and opposite axis is a minus. That is means negative. You have to use it. Even the forces, whatever you see that in the sign convention, so the forces, if it is along the direction of the x, y, z direction, then it is a positive. It's against that, then it is a negative. Similarly, clockwise is considered as a negative. If the moment is creating a clockwise rotation, then it is a negative. If it is opposite that, and counterclockwise, that is assumed as a positive. So when you want, this is a sign convention, you have to be very careful on it. You can use any kind of sign convention, whether it is a right hand rule or left hand rule, but you have to stick to that because you cannot mix the sign convention. And the first step to draw a free body diagram, identify the particle, body or body of interest, draw a coordinate axis or reference axis x, y, z direction, and specify the sign convention. Draw the, it is very important you specify, you just draw x, y, z and specify the which direction you are assuming as a force is a positive, which direction you are assuming as a moment is a positive. That is very important. Draw the particle or body or free body free of constraint. So first of all, you should remove all the constraint. Suppose there is a support, you have to replace that support with a reaction, a force. For example, you can draw a whole free body diagram, or you can concentrate part of that, a specific part, and draw the free body diagram for that particular part. So apply the external forces acting on it. Okay, when you remove the constraint, so there are external force acting on it, so you have to replay, you have to include that part of it, external forces which is acting on that boundary. Specify the dimension, angle, position in the coordinates. That's very important. So let us look at this the inclined plane. Here a block is sliding, it is counter by another block through a pulley. So it is connected to the pulley, frictionless pulley. So let us assume that when you start that, you try a XY direction. So specify that forces which is acting this way, this due to the weight of that. So you are replacing that with so there is a friction force, there is a tension in the string, so which is acting in the positive direction, friction which is acting in the negative direction, and similarly mg acting as a negative direction. So you have to do that both in the x and y components. You look at this, there is a T bar and the mg which is acting, and so you have to which one you are taking as a positive or negative. You have to specify that. Once your sign convention is specified, then you can easily. So this is the part of interest. So you can replace that with the angle which is alpha, and this is a positive, this is a positive, so this is a negative. Then this could be perpendicular, in the opposite direction, mg and this minus y would be a negative. So you have to be very, very careful on specifying the dimension. So let us we start with a very simple case about rectangular components of the force in a 2D. In this figure, the force, you look at this y, x, these are the positive, and the opposite direction is negative. So f has been resolved into components, fx along the x-axis and a component of fy along the y-axis. Fx are they called a rectangular component. So fx, the I is the that the force is the vectorial representation. You should represent force by vector. It is a vectorial component. So f of x in the I is the direction vector, and y similarly j is the vector. So total force you can represent by fx I plus fyj. So if you take that, resolve this f into x direction, y direction, this the magnitude of that fx is equal to f cos theta, and fy is equal to f sin theta. These are the unit vectors, and the magnitude is 1. So now you can resolve this into x and y direction. It's a component. So now the similar thing which we can look into the 3D in a space, basically force rectangular component. Now you can resolve this various angle. F is the force. Now you convert that, what is the fy, fh. So this is how you represent. fh is the horizontal component, fy is the along the projection along the y-axis. Then fx equal to fh cos theta. So fh is the horizontal, this one. So the fx equal to f sin sin theta y direction cos phi. So f z is equal to fh sin f sin phi sin y and sin phi. So fy is equal to f cos y. So this is the way you can represent, you can resolve a force in space on acting on a particle into various fx, fy, fz component. So now look at this another in a 3D space. If you know that if you project along the x-axis, that is the theta x, theta y, it is the angle between f and the y-axis. F and the x-axis is the theta x, and the fz is the f cos theta z, okay, that is between f and z direction. You resolve this component, you take the cos of that, the total vector can be in a vectorial representation, force can be represented in a vectorial representation, f is equal to fxi fyj plus fzk. So these are the I, j, k are the unit vectors in the x, y, z direction. So now suppose if you know the only the force of the magnitude which is acting along the no in the in any direction from if it is acting from m to n, then if you know the position of m and n, you can easily find out the vectorial component of the forces. For this is a very simple. For example, you fix your axis. What is the m? X1, Y1 is Z1, n, X2, Y2 is Z2. Now you find out what is the dx, dz, and dy. So the difference of the y different coordinates. Now you can get the what is this no length, d is equal to dx square plus dy square dz square. So now look at that vector mn. Basically mn is represented by dxi plus dyj plus dzk. So if you want to find out a unit vector of that particular direction of this vector mn, so what you have to do that mn vector divided by the magnitude of that. The magnitude of that we know that it is from the, it's a d. So now you substitute that, it is a you can get a force of the in the magnitude into the unit vector of that direction which is acting on the direction from m to n. We can get, if you know the unit vector, if you multiply with the unit vector, you will get these components of these fx, fy, fz. So you do the simple mathematics trigonometry, you look at the cos theta x is nothing but dx by d, cos theta y dy by d, cos z. If you add and square it up, it will become the unit. Basically what it says that it is the unit vector is a dimensionless quantity, so a dimensionless representation. So this way we can resolve. In fact, if you know the magnitude of the force and you know the unit vector which is acting which is on this direction, then you just simply find out the unit vector from the position vectors and multiply that with the force magnitude. You will get the resolved component of the theta x, theta y, theta z, that is fx, fy, fz. Okay, so that's how you have to go about it. Let us look at that simple problem. A tower which is tied by a cable tension from A to B. So that is, these positions are all well clearly defined. So this is the problem. Now what we are going to find out, what is the tension in the cable. So the vectorial component of the x, y, z component of the tension, and then you can find it out easily. What are the theta x, theta y, theta z of that force. So you look at that AB, that is the tension which is acting from A to B. So you have coordinates. So you fix this origin at this position, that is the, you can take it as a O. So now you find out from O is 0, 0, 0. So find out this position A. A is basically you know that from the origin how much it is distance is moved. So 30 in the if you fix it 30 in the k direction, basically that is a negative of the z direction. Y, you know this is the x, this is the z minus z, this is the y. So you construct the you construct the now the dx component, dy component, dz component, find out from the origin, and you know that what is the AB. AB, the vector is nothing but dxi plus dy j plus dzk. So AB, the magnitude is nothing but, if you once you find out dx dy z, you can find it out that what is that quantity, the magnitude quantity. Now you know the vector, the magnitude of that. So it's very simple. What is the unit vector? Lambda. AB divided by magnitude of the AB vector divided by magnitude of the AB. So now the force, you look at the force. We don't know what is that. It's the vectorial component. We know the magnitude 2500 Newton. from the problem. So if that it is the force, the magnitude of the force is I know 2500 Newton. Now what you have to do is F into AB vector divided by AB, that is a lambda. So you convert that, now you resolve that into F is equal to minus of that component f of x, this is f of x, this is f of y, that is f of z. So you can easily find out dx by d will give you cos theta x, dy by d it will give you cos theta y, dz by d will give you a sin theta y. We have this definition from this equations. So you can easily find out if only you know the magnitude of the force, you can find out the various vectorial component, resolved component, that just using a projection of the unit vector along the force, that will give you various component of it. This is the one of the simplest problem which I could discuss. So what I am going to do is this is the problem. There are you look at this diagram. There is a flying balloon, and it is tied through a string, and A, B, C, D. Okay, this is B, C, D, and A is this position. So the O is the origin. So the coordinates are specifically is given. P is the force which is exerted by the balloon. So that is the P which is acting in the positive direction of the Y, and we have to find out what is the component along the different string from B to A, or A to B, A to D, A to C. Suppose if one component is given from the equilibrium equation, easily you can find out the other component. So I'll demonstrate for the one particular problem, then you can easily solve that the remaining problem. So force at AR, basically it's given in the AR, the tensions, the TAB, TAC, TAD, and a P which is acting that. P is equal to PJ, express all other force in unit vector IJK. Now let us look at that. First is the coordinate, and this is the origin, and A is you look at this coordinate, and now find out what is the AB, AC, AD. That is the vectorial vector of that position, AB, AC, AD. So once you find out that, you find out the magnitude of that. So the vector divided by the magnitude will give you the unit vector. So the vector TAB is equal to magnitude of the TAB into the unit vector. You will get the three equations, TAB, TAC, TAD. So we know from the equilibrium condition that the sum of the total force equal to 0. Also you have to understand that in the x, y, z direction, I, j, k direction, individually the forces, sum of the forces equal to 0. So if you substitute this value TAB, TAC, TAD, whatever we get it into the plus PJ into this equation, so what would happen, you equate the IJK component to 0, you will get it, because the TAB is known, TAC 479, TAD, okay, this is TAD, TAC. So you will get this is a D, okay. You just understand that P is equal to 1031 Newton, okay, 1031 Newton. So just remember that finding out the unit vector and projecting that unit vector along the force, magnitude of the force, it will give you the force vectors. Finally you have to add all these vectors, force vectors, and make it as 0, because it is in a static equilibrium, it is a tide that, so so it is in a static equilibrium, so it is sum of the forces equal to 0. Then you replace that with ij component individually, x, y, f of x, sum of the forces in x direction, sum of the force in y direction, sum of the force in z direction also 0. So this is how one should take these and approach and solve that. It should be a systematic. So you are using the sign convention, you are using the you are finding the unit vector and projecting that unit vector along this force and the magnitude of the force, and you finding out so using the equilibrium equation, so everything. So the sign convention, the free body diagram, here the free body diagram, you can basically you are replacing that with the full free body diagram. Basically you can replace that in this what is happening individually. You can deal it, but this is better you handle this way. That would quickly converge the solution. So I hope you understand that how to solve static the problems in a static equilibrium condition, whether it is a particle, whether it is a body in rigid body in no space. So you can easily solve that using static equilibrium equation, force equilibrium equations, and moment equilibrium equation. Just simply apply this, and you can easily. But follow the systematic procedure in the examination. Follow these steps. First draw the coordinate, sign convention, free body equilibrium equation, and whether it is a rigid body, then you have to put if you have less number of equations, then you can. So I hope, dear students, you will do well in the examination solving this problem.
Hi students, in continuation to these statics problems which we solve, today we let us look into this one more problem which is very important. This is one of the problem which give the idea about using equilibrium equation to solve unknown forces and moment. This is a force and a couple combined problem. You can understand all the concept of 2D, 3D equilibrium equations and extracting the estimating the value of forces in x, y, z direction. As I said that any vector quantity like a force is associated with the direction. The sense of direction, as the direction can be found, you can determine the direction of that force using the unit vectors, determining the unit vector and the direction, and multiplying with your magnitude of the force, or you can use the angles at which the force acts, resolving the x, y, z axis, or you can use the slope at which the force acts. So the unit vector can be extracted, or you can estimate the unit vector either using a position vector or the force vectors or any other vectorial quantity of that directions. So if you see here, this is the force and couple of force stop problems. You see that brackets which is in a three-dimensional attached to a wall. There are cables which is also attached. So now replace the what we are going to solve is replace the force exerted by the cable with an equivalent force of force coupled system at A. So what is the equilibrium condition if you take these forces which is acting on different direction, and what kind of equilibrium condition at A could satisfy the equilibrium equation. Both the force, sum of the forces and the moment has to be 0 to maintain the equilibrium conditions. So we look into that. There are x, y, z direction, and there are positions which are mentioned. There are angles mentioned. The force which is acted D, B to E, and there is C. At C there is 1000 Newton which is act. At B 700 Newton acts. At D 1200 Newton acts. So there are positions vectors. Positions are given. So from that we can estimate what is the unit vector and project that unit vector into the force scale magnitude, and then finally we will get all the xy direction. From that we can set a equilibrium condition. What is the equilibrium condition? Sum of the forces in x direction and y direction and z direction independently 0, or some of the forces. Similarly, the moment at A should also be 0. This is how we are going to determine if we set the condition of the equilibrium. So let us see that. First, what we have to do, draw a free body remove the constraint, and we have to if you draw the free body, if you see that, first we know that what is the FB. If you look into the FB, it's a 700 Newton which is act. So you have to multiply with the unit vector BE. If you want to find out the unit vector BE, so first the vector, what is the vector BE, and the magnitude of the BE. So that if you found, extracting from the using the x2 minus x1, y2 minus y1, z2 minus z1 of ijk of that direction. I is the x direction, j is the direction, k is the z direction out of the plane. Okay. So if you look into that clearly, you will get that lambda b. So 75I minus 150j plus 50k. So divided by that magnitude of that is 175. So similarly, now if you find the vector AB, AC, AD, we will get these parameters, and the unit vector for that each direction we can similarly find out the magnitude, corresponding magnitude. The vector divided by the magnitude will give the your unit vector in the direction. So if B is equal to 700 lambda b, so multiply with that, you will get FB. FC, FC is you resolve x in z direction, and y direction is not there, the force set. Similarly, FD is x and y direction, z direction is not there. So the sum of the forces, if you make it, so adding these forces to maintain this equilibrium condition, the resultant forces has to be to be add all the x forces, y forces, z forces. What do you get? The resultant force is 1607 Newton, and the 439 Newton, 507 Newton. The resultant force, it has to be there so that to maintain the equilibrium. 1607 Newton and 439 Newton and 507 Newton. That is in the z direction, which is opposite of the positive against. So that's how we get a resultant force. So now, if you move to that, to finding out the moment of that each forces acting at A, so you have to multiply with the force, the position vector, and the cross product of the position vector and the force, corresponding forces. So to do that, it's a very simple method is because it's a vector quantity. So ijk is the vector, unit vector in the directions. Respective direction x, y is z. Similarly, the value of r and the value of force. If you do that cross product and find out, it is finally r of that BA or AB vector in the FB is equal to 30I minus 45K. Similarly, CA vector in the FC is equal to 17.68J. And similarly, if you add AD and cross FT is equal to 163.9K. So the moment has to balance for the equilibrium, the moment at A should be 300 Newton that meter is ith directions. So and 17.68 Newton meter is in the jth direction. This is a torque. So and 118.9 Newton in the meter, that kth direction. So this is the kind of moment and force required to maintain the equilibrium conditions. So if you wanted to represent, you see that anything which is act in xy direction, the resultant rotation would be in the k direction. So why it is minus sign means that is in the clockwise direction. So anti-clockwise directions are a positive quantity. So if you add this thing, and then what we are getting is finally it's a kind of torque at A, and the force corresponding the force also is given x, y, z direction. What is the force that is resolved into? So this is the way you have to approach any problem of the statics, whether it is a 2-dimension or 3-dimension. You must understand that you have to basically find out the component of the forces, or find out the resultant forces, adding this component of the forces, find out the resultant forces, and find out the unit vectors, and projecting that to the magnitude of the force. That would give you a vectorial representation of the force in the x, y, z direction. I hope you understand this, and if you practice, if you understand this problem, you can solve any problem in the statics, whether it is a 2-dimension or 3-dimension. This is a very key problem which you have to practice and understand. Thank you. I hope you do well in your examination.
Hi student, I hope you are doing preparing for the examination very well. My best wishes. You just look into this some few problems that may help you do well in the examinations. This is especially about the industrial expect torques and the problems in a rigid body in a plane, the motion of rigid body in plane. If you look into that, a rigid body is a non-deforming. This is just like that, what you are seeing. If you apply many forces component around that, for example, there are many directions you can apply a force in a plane. You think about a plane. So if that is the rigid body, it has the geometrical center, that's the mass center, center of mass. If the various forces act on it, what would have happened? This body will be translated as well as rotated. Depends on the how these forces can be resolved whether it is it's both in a translation as well as in the rotational motion. This is what you see that in the rigid body, the G is the center of mass center, and F1, F4, F3 is acting in a plane in the rigid body. You can resolve these forces into a torque about the center of mass and the translation motion in the of the center of mass. That is M into A. A is the acceleration of the center of mass, and H is the rate of change of angular momentum about G. So that is nothing but a torque. So the angular momentum of the rigid body about its mass centers. If you rate of change of that will be a torque. Specifically this kind of forces you can resolve in the x direction and y direction, and the moment you can write as a moment of inertia and this angular acceleration. Some of the forces in FFX related to mass and acceleration in the x direction of the center of mass, and the y direction, similarly in the y direction, mass and acceleration in the y direction. So that's what we call it as a D'Alembert's principle. So any rigid body motion in a plane motion of the rigid body, so you can resolve into a translation as a force in the x and y direction, and the moment you can resolve into I into alpha, that would be in the out of the plane, the direction. So let us look into the simple problem. This is the equation of motion of for a rigid body. When the forward speed of a truck as shown was 30 feet per second, so the truck moves at 30 feet per second. When the brakes are suddenly applied, causing all the four wheels to stop rotating. So you are applying a brake, the wheels are. So what would have happened? Truck probably a skid.
it's getting, because of that sudden break. So when it stops, there is still a momentum which that would cause a skidding, rate of change of momentum. Okay. So the truck is skidded to rest at 20 feet. After the brake applied, it just is skidding to the 20 feet. So the question here is determine the magnitude of the normal reaction and the friction force at each wheel as the truck skidded to rest. So here the friction is involved, the kinetic friction is involved, and there is a normal force. So what you have to do is there are four wheels, because it's a plane, in a plane motion of the rigid body in a plane. So you can consider a two-wheel system, and finally you can divide that force because it's a symmetrical nature, where G is the center of mass, center of gravity, whatever. So here, because the gravity acts. So now what you have to resolve these into forces and moment about A. If you take that equation, equilibrium equation, you can easily find out. Before that, you supposed to apply equation of motion to find out what is the acceleration in the x-axis. So because as soon as you apply a brake, there is a deceleration, so it has to travel 20 feet to come to a rest. So that you take into account using the u square initial speed and the v square, the 2ax. That is the kind of equation of motion you are supposed to use to find out what is the ax. So v naught, we know that 30 feet per second, and v square is equal to u naught square plus 2ax. You know that it's come to rest, so that the final velocity is 0. So you substitute that, you find out what is the a. A is the deceleration, it is a minus 22.5 feet per second square. So now you know that there is the acceleration, deceleration which is acting, there is a velocity, and what is the normal reaction? It is just a weight of the act at the center of gravity, at G. So you can easily find out what is the it is a mass into G, acceleration due to gravity, that is given. So you can now you think about, you resolve in a y direction, x direction, and if you look into that, the normal reaction at A, normal reaction at B minus W is that, because if you look into this directional, the right hand direction, which we are doing all the problem. So counterclockwise moment is positive, clockwise moment is negative, force upward is positive, downward is negative, right hand side is positive, left hand side is negative, out of the board is positive, into the plane is negative, so something like that. So you have to take the sense of direction. Here it is mentioned. So friction force Fa plus Fb, because which is act against the the motion. So you take a negative signs. Similarly, this is a deceleration, m into a. So you finally you will get Fa plus Fb is equal to mu k into Na plus Nb. This is comes from your friction, kinetic friction constraint equations. So that's equal to mu k into W, weight of the vehicle. So from that you can find out, you know that acceleration due to gravity in feet per second square is 32.2. So substitute that, you will get a mu k is equal to 0.699. So now there is some parameters which is still we need to undertake, which is we can't still there are some unknowns we need to estimate, especially NB. What is the NB in terms of W? So now if you take the moment at A, so you will get know that what is the NB in terms of W. So Fp is equal to mu k into Nb. So finally you will get Fb is equal to 0.454 W. That is the weight of the vehicle, of that friction force which is acting into point B. Similarly, if Fy, if you take that Na, you will get it, and Fa is equal to mu k into Na. So the finally it is a 0.245. So in each wheel, if you look into that, in each wheel you have to divide it by 2. So you will get what is the front wheel and the rear wheel, what is that in terms of W, because W which is the weight of the vehicle, which is not given, but you can still assume that it is a known parameter of W. So this is how you have to. So let me again emphasize that
as soon as you have the problem, you have to draw a free body diagram and resolve these forces in the x and y direction and take the moment if there is an unknown component. From that we can converge very quickly to that what is this needed and that. So now we see the second case, the second problem. Car shown in this figure has a mass of 2000 kilogram or 2 capital mg. The center of mass at g determine the acceleration if the rear driving wheels are always slipping, whereas the front wheels are free to rotate. The condition, the constraint here is if the front wheels are free to rotate, means there is no friction. The rear wheels are slipping, means there is a friction. Neglect the mass of the wheels. The coefficient of kinetic friction between the wheels and the road is given here. So you know that. So now what you have to do immediately, take this dimension and apply the load condition and draw the free body diagram and fix your coordinate system as it's given. So these are the 2000 into 9.82 Newton, these are the parameter. So now you resolve that FB, FA is not there, as I said that there is a free to rotate, means reason the front wheel is a zero friction. So FA is equal to 0, but there is a still, it's the reaction force NA, NB, AG, there are 3 unknowns are there. So you have to take the moment at either G or any one of these point A or B to solve this. So let us again we just to put into the practice that what is f of x, mass in the acceleration, that of what is f of y, mass in the acceleration in the y direction. So if you substitute that 0.25 NB is equal to, that is the in x direction the friction force is equal to 2000 into AG. Similarly, Fy is equal to be substitute NA plus NB minus 2000. So you know that NA and NB in terms of 2000 into AG. So if you solve that, you will find out the moment at G. You can take a moment at A or moment at G. So it depends on moment at B also you can take. So whether it is quickly converged. So a moment at G is given by NA, the normal reaction is 1.25 m and minus 0.25 NB into 0.3 m plus NB into 0.2. So the sign convention basically it's a clockwise negative, anti-clockwise positive. So based on that you have to put, finally you arrive at AG. What is the AG? Is 1.5 meter per second square, that is the acceleration in the x direction. But here it is a kind of deceleration or if it is a positive, this quantity is positive, so the vehicle is in this direction, so you can take that. So NA is equal to 6.88 kN, NB is equal to 1, it's kilonewton basically, kN is a kilonewton. So this is how, as I said that you can take it at MA also to find out that, so you will converge the same result as I said that. So so you have to be little care about the direction, sense of direction when you take. So these are the quantity NA, NB and acceleration at G. That's what your so you can solve in a but you have to consider that resolve that forces in the x and y direction of the center of mass and rotation about the center of mass or center of gravity. So that's how it is converged, and either you can take it as a or and B or a G, depends on how. But this equation is going to be, if you are taking it a G, that some of the rotation is not about G is 0. That's what it is given here. Some of the because the vehicle is not rotating about the center of mass, so that's 0. That's how you have to solve it. Similarly, this third problem which I'm talking about is a motorcycle shown in a figure has a mass of 125 kg and a center of mass at G1. There are two center of mass. One is the vehicle center of mass, and the G2 is the the rider, the driver center of mass. So you have two different center of mass, and these positions vectors are given A and B. And now also you have to apply normal reaction and the weight, sum of the weight and both the center of mass
So that is towards the, in the negative direction. So if you see that the wheelie, the term wheelie, that's why you have to read very carefully. The wheelie, the term wheelie is is rising is the front wheel. So the friction at the front wheel is a zero. Neglect the mass of the wheels and assume that the front wheel is free to roll. So there is no friction. That's what it is. Emphasize that. So let us draw the free body diagram and apply the forces and resolve the forces. So we have to find out the NB and NA is a free wheel. If you assume that it's a free wheel, it's above the ground, then there is no normal reaction. So the NA is 0. So NB, FB, AG, we have to find out. There are 3 unknowns. So similarly resolve that in the MA, AG, in the X direction, MA, AG, in the Y direction. Now you have to take, because A doesn't have contact with us, so you have to take a moment at B, because you are raising the bike up, so the moment comes at B. So you resolve that, apply that 75 kg in the AG plus 25 kg in the AG is the FP. NB is equal to minus 73.5 minus this much is equal to 0. If you take this equation, F is the equations. So from that you can easily solve that AG is equal to 8 point. This mass, the acceleration at the center of the mass center location is 8.95 meter per second. NB is equal to 1962 Newton, and F is equal to 1090 Newton. So dear friends, solving the problem is you have to systematically approach and solve that each and every time, which is not known, and there are known parameters given. Do it carefully, and nothing to be worried about, but you have to systematically approach that. And so my best wishes, and do well in the examination. Follow the simple professional procedure. As an engineer, you have to systematically solve this problem, and it has to be neat presentation, and there should not be any scribbling, and draw the free body diagram, and fix your coordinates, and direction, sense of direction, right and roll, you can take it as, and then resolve the forces, take a moment if there is any unknown parameters are there, you can easily solve that. Thank you. I wish you all the best.